Hi there. In this video I will go through the working out for one of the versions of the Chapter 3 summative test. In question number 1, we are looking for the logarithmic form for this given exponential form. The base is a, the exponent is m, and the power is w. So we know that base raised to exponent equal to power can be rearranged in log form as the log with a base of b of the power, which is called p, and that isolates the exponent, which is exp. So in this case, we're looking for log base a of w. Log base a of w is equal to m is c. Here we're talking about the 100th power of 99. So we have the 99 family sequence, 99, 99 squared, 99 cubed. And so we're really looking for 99 to the exponent of 100. The whole thing, base to the exponent, is the power. So the 100th power is 99 to the 100. So in number 3, the only exponential growth function is one where we have a base which is greater than 1. Now it's also important to notice that we have to have an exponential function and not a power function or logarithmic function. So we can't have this logarithmic function and we can't have this power function or polynomial function because the variable is in the base. We are looking for the variable to be in the exponent. And so exponential functions only have variables in the exponent, which is either b or d. And in the case of b, we have 3 to the negative x, which is 1 over 3 to the positive x plus 1. So in part b, we have that the base is equal to a third, which is between 0 and 1, so this is exponential decay. And in part b, we have the base is equal to 3, so we have exponential growth for part d. In number 4, which function is the inverse of y equals e to the x minus 7? So the first thing to do to get the inverse is to swap x and y. So when we swap x and y, we end up getting the inverse equation directly, x equals e to the y minus 7. Now that's not one of the options because every option has had y isolated, so then we isolate for y, or we solve for y. Now whenever we solve, we undo what's being done to the variable in the reverse order of operations. So in this blue equation here, the first thing being done to y is exponentiating base e, and the second thing being done to y is subtracting 7. Technically that subtracting 7 is being done to e to the y because we now have y has been exponentiated base e. So when we solve, as always, we undo these steps, but we perform them in the reverse order. Imagine that y is like your foot and it got dressed in the morning. You put on a sock, which is the innermost layer, and then you put on a shoe, which is the outermost layer. Then to undress your foot, you have to do the opposite of these steps. The opposite of putting on the sock is taking off the sock, and the opposite of putting on the shoe is taking off the shoe. However, you can't take off the sock before you take off the shoe. So when we solve for y, we first have to do the opposite of subtracting 7, which is adding 7, and then we have to do the opposite of exponentiation base e, which is logarithmication base e, or applying the natural logarithm, ln. So the first thing we do to both sides is to add 7. And the next thing we do is to apply the natural logarithm to both sides of the equation. So ln of e to the cancel, and we're left with y, and y is going to equal the ln of x plus 7. Now if I didn't have x plus 7 in brackets, this says that we apply ln first and then add 7, which is swapping the order of the operations. So there have been most of the mistakes in this entire test actually have been about violating the order of operations, and that goes way back to conceptions and misconceptions in Algebra 1. Number 5 was probably the best answered question, and in this case to invest P dollars in an account of 12% per year compounded quarterly or compounded 4 times per year, we know that n is equal to 4, and so from A of t equal to P times 1 plus r over n raised to the exponent of nt, we have r is equal to 12%, which is 0.12, and we have P times 1 plus 0.12 divided by 4 is going to be 0.03, all raised to the exponent of 4 times t. And so that gives us the answer of D. In number 6, we have an exponential function because the variable x is in the exponent, and furthermore, the base is equal to e, which is approximately 2.718, which is more than 1, so we have exponential growth. And because we have an exponential growth function, the graph looks like this, and we have a horizontal asymptote on the left end, And furthermore, the horizontal asymptote is this constant, so y equal to -4 would be the horizontal asymptote moved down 4 spaces, let's say like this. And the answer is A. Now, in another form, we had a base of 1/2, which is exponential decay base, because the base is between 0 and 1, and so we would have a right-end horizontal asymptote. In number 7, we want to solve for x. Since x is in the exponent, this is an exponential equation, and we undo what's being done to x, which is apply log base 3 to both sides of the equation. There are other approaches to solving this equation, and one might be just to apply natural logarithm directly, and we see that log base 3 of 10 is none of these answers. So we have to be careful, because log 3 means log base 10 of 3. If we wanted to change the base to 10, we wouldn't get this answer. So we could change the base to natural logarithm, or rather to base e, so we would get log base e of the top power, which is the 10 here, over log base e, or ln of 3. So the answer is D. Something that's happening here a lot, again, people are violating the order of operations. A lot of people are, in a way, factoring out a ln here, and they're making this the ln of 10 over 3. And so some people are thinking that ln of 10 divided by ln 3 is the same as ln of 10/3. That's not true. And in other cases, people are thinking that these are like factors that join by multiplication and can be divided. That's also not true. The answer is not equal to 10/3 because we cannot undo or factor those. So again, be careful of the order of operations. In number 8, we're really talking about using exponents to help us to represent really large numbers, or in the case of concentration of solutions, really small numbers on a more human-sized scale. So the concentration of hydrogen ions is a really small number, something like 0.000 something. And if it has a pH of 4.2, we want to work backwards to get the concentration. So we know that the concentration of hydrogen ions is equal to 10 to the exponent, which is negative the pH. And so the pH is given as 4.2, therefore the concentration is 10 to the negative 4.2. And that would be measured in moles per liter. Here we can rewrite ln as, or natural logarithm as log base e of e, or not. I'm just going to recognize each of these expressions, these powers, is e to some exponent. So we're going to have the ln of e to the negative 1 plus the ln of e to the 0 plus the ln, or the log base e, of e to the 1 plus log base e of e squared. I've just rewritten ln as log base e in order to be a bit more clear, or a bit clearer on the base involved. So I could do that for all of my natural logarithms, but I don't have to. Every time you see log base something of something, you read it as, what is the exponent on this base to get that power? Don't forget that exponents can come down in front as coefficients, and so this is going to be -1 times 1, which is -1. What is the exponent on base e to get e to the 0? Well, that would be an exponent of 0. What is the exponent on e to get e? Well, that would just be 1. And what is the exponent on e to get e squared? That would just be 2. And so the answer is 2. And in the last question for the multiple choice, we want to condense the following logarithms. We see that there are 3 logarithms with a positive coefficient, so these will all have powers that are joined by multiplication. But first, this exponent needs to come up as, or coefficient needs to come up as an exponent on c. And then we have 2 negative logarithms, which means that their powers will be in the denominator. So for this particular one, we end up getting a single logarithm with the like base of w. We're going to get a fraction. So we're multiplying the powers of a, b, and c squared. And we're going to be dividing by d cubed, because another way of seeing that would be for this negative to come up as an exponent here of -1, which means reciprocal, which means goes in the denominator. But I'll just leave that with a negative in front of the logarithm, which means we are dividing those powers. So we're going to divide by d cubed. We're also going to divide by 5e, so I'll just put the 5 in front in the e second. And for extra clarity, I'll put brackets around that. And we have our answer here of D. In number 11, we're just working with our basic number facts. Many people need a lot more practice with the basic number facts, knowing what the powers, squares, and cubes are, and also with the logarithm laws and exponent laws to help rearrange expressions. This was another place where the order of operations was misunderstood, and Basically, logarithm laws were made up in favor of the actual logarithm laws. So in the first case, this is saying, what is the exponent on base 8 to get 128? We should recognize that both 8 and 128 are powers of 2, and so we can use the change of base formula in favor of the new base of 2. This is the simplest way to work this question out. However, there are other ways. Some people chose to set this equal to x and then rearrange to exponential form. This is fine. However, a lot of people changed to exponential form without actually letting the first expression equal x, which meant that solving for x was in no way related to the question because the question did not have an x in it. Here, all we're really doing from the exponential form then is changing the base. So we recognize that we have 2 cubed all to the x equals 2 to the exponent of 7. A lot of people didn't know that number fact or had kind of the 256, 512. They didn't know those numbers very well, and so there were problems there. However, directly from the logarithmic form, we can change the base and ask, what is the exponent on base 2 to get the power of 128? Well, that exponent is 7. And what is the exponent on base 2 to get the power of 8? That exponent is 3. So the blue answer is the most direct, most succinct way of working this out. This is fine as long as make sure that you let x equal the original expression. So when you solve 3x equal to 7, x equal to 7/3 is actually related to the original question. In the next one, we have log base 10 of some power of 10. Make sure that you're putting an equal sign in front of each of these logarithm or in front of each line. These expressions are all equivalent and they should be linked as such. We have log base 10, which you didn't need to write, and this is going to be 10 to the exponent of -5. Then we have log base 2 of 32. You can rewrite it if you want, or you should probably just know that that's equal to 5. And then 1024 is actually 2 to the exponent 10. So this is going to be minus the logarithm of 1 over the 7th root, which is an exponent of 1/7. And this is 2 to the, this is base 2. This is 2 to the exponent 10. So we see that the first logarithm is equal to -5 and the second logarithm is equal to 5, so that will be 0. You don't need to put equals 0 here because that would not be well communicated. Put the 0, or indeed don't write anything, underneath. So we're working down in a column to get the most concise, precise communication possible. Now let's just keep using our exponent laws to rewrite 2 to the 10 all to the 1/7, which is going to be 2 to the 10/7, and then the 1 over it means this is going to be 2 to the exponent of -10/7. So we're going to get 0. We can just not write anything down. You can cross them out if you want. Some people change multiplication to or addition to multiplication and make all sorts of adjustments to the question. Probably one of the most common things that people did was just say, okay, well, these have the same base, so let's just combine them. But even more direct and even simpler than that is to recognize that you can evaluate those basic logarithms, but you need to know your basic number facts and you need to know your exponent laws to see how to rearrange things. So that's going to give me 0, so I'm going to have negative times the exponent that you put on base 2 to get 2 to this exponent. So negative times -10/7, and the final answer for this particular version is 10 over 7. The next question I think was common for everybody. We had log base 6 of 18 plus log base 6 of 12. Make sure you don't change the base or change the question, and if we're adding two exponents, which each of these is, then we multiply the powers. We keep the base and we multiply the powers. Now a lot of people took pains to multiply 18 times 12, and well, most people got it right, not everyone. And we got 216, but I'd like to encourage you to see another way to work this out. 18 times 12 is going to be 6 times 3, and then 12 is 2 times 6. And when we group these together, we see 6 times 6 times 6, which is 6 cubed. And so we're going to get log base 6 of 6 cubed, which is equal to 3. A lot of people didn't finish that off because you don't know your basic number facts. You need to know these things. Okay, for the next question, we have a change of base formula. We could actually write it as log base 2 of 8, or we could have changed it to a fraction of 2 logarithms with whatever base we want. And this is one we've seen over and over and over again in the course, in the videos, and we get 3 divided by 1, which is 3. In the next question, again, a lot of people set this equal to x. You could work on part of it at a time. You could just look at the exponent. But ultimately, we have a 5 to the and a log base 5. We want those to be one after the other. We want them to be right consecutive functions if you want, one after the next. So 5 to the log base 5 we know will cancel. In order to make that happen, this coefficient of the logarithm needs to become an exponent on this power of 9. So we're going to get 5 to the log base 5 of 9 squared. And this gives us 5 to the log base 5 of 81. And I'll just talk about kind of the heights of things here. There's some difficulties knowing what's in the exponent and what's on the ground and what's at what level. Oftentimes I'm seeing people write logarithms and they're putting the base, so for example if I had log base 2 of 8, I'm seeing log 2 and then an 8 raised up. You have to really make sure you know what number is on the ground, on the main level, as a subscript or as a superscript. So pay particular attention to your feedback on your paper, because I've gone through that pretty much for each person. And so we'll have 5 to the and log base 5 will cancel. Remember, there's an automatic 5 to the, if I were to write this like this, 5 to the log base 5 of 81. This is a function and its inverse function which cancel, and so we're left with 81. Normally I would put it here, but I'm running out of room, so I can work to the side. Make sure you're following a similar format, keeping it nice, neat, and clear. Otherwise, it's really difficult to follow and difficult to get a good communication score. Here, again, we want the bases to be the same, so we have a 9 and an 81. We can rewrite the 81 as 9 squared, and we can do it in stages. 9 squared all to the 100 like this becomes log base 9 of 9 to the exponent of, the exponent laws here say to multiply the exponents. And what is the exponent on 9 to get 9 to the 200? Well, the answer is 200. Now, the ways I've shown here are not the only ways for working this out, but they are the most direct. So I encourage you to rework each of these questions, even if you got it right, because the communication in general needs more practice and more polish. And number 12, we want to determine the domain of the function. It's probably one of the simplest concepts for people, but it was poorly done because mostly we didn't use the word and where we needed to. The domain requires that powers must be positive, and as stated in our videos on logarithms, before we use any of the logarithm laws, we must first work out the domain. A lot of people immediately rewrote that as the logarithm of one power divided by the next, but that's not entirely true because these functions have different domains. So if this is a red function, the domain of the red function and the domain of the blue function are not actually equal. And so we want to make sure that we're getting the right domain here. Okay, since I've color-coded my function now in red, I'm going to make it all in red. So we know that we've got two powers. We've got x plus 3, which must be positive, not negative. Some people said not equal to 0, which is not correct. We also need the second power to be positive, and then a lot of people were ambiguous. They did not indicate and or, but the and is absolutely crucial here. So we end up getting that x is greater than negative 3. And I just wanted to talk about the solving here. A lot of people are working really hard. Negative x is greater than negative 5, and then x, don't forget to flip the inequality sign, and 5. Why don't you just do it in one step? We can just take the negative x to the other side, so we get 5 is greater than x. Because of the and, we have to consider the intersection of those two sets. One I will make green, and the other one I will make purple. So the purple set is when x is to the left of 5. The green set is when x is to the right of negative 3. And because it's not enough for one power to be positive and not the other, they both must be positive, we have that the set that is in the intersection is between negative 3 and 5. Now, unfortunately, a lot of people got the right answer, but without the and, the logic just does not follow. So don't cut corners, because this is marking you down for both concept and procedure and for communication. So the domain is x contained from negative 3 to 5. Now, every time we have a logarithm equation or a logarithmic function, we have to consider domain. So when we're solving here, solving for x in the first question is solving an exponential equation. Solving in part B, we have x is in the power. We're taking the logarithm of x in the power, so we have a logarithmic equation. Here we definitely have to consider domain, but we might also consider that we should always think about domain. In fact, if we had always, since solving linear equations, if we had always solved for the domain, it wouldn't be a novel thing all of a sudden. We would have always established that habit. So in fact, you should always think about domain before you solve any equation. The thing is, exponents don't have any restrictions. Exponents are contained in the reals. And so therefore, x can be contained in the reals. We have no domain restriction. Meanwhile, over here, x is in the power, and we know that powers have a restriction. They can't be 0 and they can't be negative. And therefore, we are going to have a domain restriction. Over here, the power is x minus 1, which must be positive, and therefore x is greater than 1. Notice that x by itself is not the entire power. X is in the power, but x is not the power. X minus 1 is the power. This will play up in number 14b when we see that in a minute. Okay, so we don't have to worry about domain any further. We can go ahead and solve. Some people decided to let this internal expression equal a, which is fine. If you don't, you just have to make sure you're following the order of operations correctly. So 3 times 5 to the negative 2x is equal to 1. We can divide both sides by 3. And I really like the idea of recognizing that 1/3 is equal to 3 to the exponent negative 1. Then we can reciprocate, just going to imagine we didn't have this, we can reciprocate both sides of the equation by raising to the exponent of negative 1, which is the same as doing 1 over. We multiply those inner and outer exponents, so we get the very simple equation with whole number base and power of 5 to the 2x is equal to 3. Then we can undo exponentiation base 5 by applying log base 5 on both sides. Or you could simply immediately rearrange from the blue exponential form to logarithmic form. The base is 5, we take logarithms of the power, and we get the exponent. Then to solve for x, and of course let me just say log base 5 and 5 2, that cancel, so that we get the 2x is equal to log base 5 of 3. Then we divide both sides by 2, and therefore x is equal to log base 5 of 3 over 2, or 1/2 times log base 5 of 3, which is simple. Or we might even take that the coefficient of 1/2 and bring it up as an exponent on 3 to make x equal to log base 5 of 3 to the 1/2, or the square root of 3. This is very tidy, very simple. In general, the fewer symbols and notation, the less ink we use, the simpler the expression, or the answer. Now here we could compare against the domain, but x can be anything, and so this is valid. So let's take a look at the next question with the same point of view of undoing what's being done to the variable step by step. One of the gross misconceptions here is that people took the logarithm and they somehow distributed it through the brackets. We can't do that because logarithm, well, first of all, if we had ln of x minus ln of 1, we would be able to condense that into a logarithm of x divided by 1. And so we're really blurring the lines to saying that if these three expressions are all equal, then if these two circled expressions were equal, we're really saying that x minus 1 equals x divided by 1. And that's not true. So which does ln of x minus ln of 1 equal? Does it equal ln of x minus 1, or does it equal ln of x over 1? Well, this is the correct one because this is our logarithm property, which comes from the inverse of the exponential property. As a reminder of that property, if we had x to the a divided by x to the b, we would keep the common base or the like base and we would subtract the exponents. So here we are subtracting exponents or dividing two powers. Here we are subtracting two exponents or dividing two powers. So each of the logarithm laws stems from the equivalent or associated exponent law. We need to know the exponent laws really well to be good at the logarithm laws. So don't do this kind of distribution. That is not a valid law. You cannot do that. So I've mentioned on a lot of people's paper that there's been a violation of the order of operations. If we think about the steps being applied to x, or the operations being applied to x, let's just write them in order. The first thing being done to x is what's in the brackets. We're subtracting 1. And the next thing is applying logarithm, applying log base e, or applying the natural logarithm ln. This is not a multiplication, so you cannot divide to undo it. Then the third thing is we are subtracting e. So if we want to solve for x, we have to undo each of these things. We have to add 1. We have to apply the inverse of logarithmication base e, which is exponentiation base e, and we have to do the inverse or the opposite of subtracting e, which is adding e. But importantly, just like watching a movie in reverse, not only do we see the opposite steps, but we see them performed in the reverse order. So the first thing we need to do to both sides of this equation is to add e. Now we can show the adding of e, or we can just show the result. Once upon a time, we used to do plus e plus e. I see a lot of students still do this. That's okay, but you do want to kind of move on to the stage where you're skipping some of those steps because they should be practiced by now. We've been doing these kinds of steps since Algebra 1. So we've undone subtracting e. Now we have to undo the logarithmication base e both sides. And the inverse of logarithmication base e is exponentiation. So we make each side the exponent on the base of e. And the whole purpose of that is because e to the and log base e will undo or cancel each other, leaving us with x minus 1. But on the other side, we have a new expression. We can't still have e because we've changed the left side. We have to change the right side. So we get e to the e, and lastly we add 1 to both sides because we're going to undo the subtracting of 1. And when we do that, we end up getting that x is equal to e to the e plus 1. Now, I want to just double check that this falls into my domain. Otherwise, we would have what is called an extraneous root. Well, we know that e is about 2.7, and we're raising that to the 2.7, so that's already bigger than 1, and then we add 1, so definitely this solution falls inside the domain. Question 13 solving, just go back and look at them, were a bit simpler. X shows up only once in the equation, and so getting the answers to here, but not getting the answers to number 14 would indicate that you're up to a B level for concepts and procedures. We'll notice that in part A and part B, X shows up more than once, which makes the solving a little bit harder. The first thing we would always consider for all solving, even back to Algebra 1, is the domain. Exponents are contained in the reals, and therefore our domain here would be all real numbers for X. And so we can just go ahead and solve. Meanwhile, over here, the domain has a restriction. We know that powers must be positive. I would like to see you write what the condition is first and then the algebra condition substituted in. So here we have x plus 2 greater than 0 and, which again most people missed out, x minus 1 greater than 0. This goes back to a set notation worksheet that we saw in Chapter 1 to help us revise the Algebra 1 information. Here when we take a look at these two sets on a number line, we see that they overlap only when x is greater than 1. So if I did one set in red and the other set in green, we want red and green, which only occurs when x is greater than 1. So our simplified domain is x greater than 1. A lot of people will just automatically choose a positive value for x, but that's not true. For example, x equal to 0.9 is positive, but it would not satisfy the equation because x equal to 0.9 is not in the domain. Okay, let's go back to the first question. There were a lot of violations of the order of operations here, almost too many for me to count. One thing is a lot of people added 9 to both sides, which is okay, but then somehow they took the -8 and the 9 and they made a 17 out of that. I don't know how you can separate the -8 from the multiplication here and then just add 8 to the other side. That doesn't work. Another big problem that I saw was people ignored the fact that we have to do exponents before multiplication, and this got turned into 24, which is wrong. You can't do multiplication before the exponentiation. Because we don't know what x is, we can't actually work out 3 to the x, which means since we cannot do the exponent first, we don't get to do the multiplication. There are other things. People took terms to the other side. I saw some people subtracting 9x from both sides, which again is not wrong. And then dividing by -8, which is not wrong, except I saw some people turning the -8 into a 3. And if you don't show things on both sides, it gets mixed up, and I saw people dividing by 3 here, and then somehow the -8 just disappears because it would be convenient for it not to be there. then 9 divided by 3 is 3, but 9x divided by 3 does not equal to 3 to the x, which is what I saw. There are so many variations on wrong things to do here. Make sure that if you didn't get it right, you understand what you did wrong, and please check with me to see how to fix it. Okay, so the first thing to notice is how we can get the same base. A lot of the questions that we've been dealing with exponential and logarithmic solving and expression evaluation have had to do with having different bases. And 9 and 3 are part of the base 3 family. We can write 9 as 3 squared, and that's all to the x. And then we can change the order that these exponents are applied on 3. So we can write this as 3 to the x all squared minus 8 times 3 to the x minus 9 equal to 0. And from here we have a repeated expression. We get the repeated expression of 3 to the x in the equation that we could let equal to a or some other intermediate variable. When we do that, we end up getting a quadratic equation in a squared minus 8a minus 9 equal to 0. And it's because we have the quadratic that we need to have equal to 0, and we don't take the constant to the right-hand side. Don't drop off the equal to 0. Don't turn an equation into an expression. Make sure that you have the equal to 0. Then we can factor, and we get a minus 9 times a plus 1 equals 0. And therefore, either the first factor equals 0, which means a equals 9, or this is as important as the and for the domain question, so please make sure to put it there. Or the second factor equals 0, which means that a equals negative 1. We can then back substitute a with 3 to the x, and we get 3 to the x is equal to 3 squared, and by the one-to-one property, x equals 2, which is part of the domain of all reals. Or 3 to the x is equal to negative 1. And if we were to think of this graphically, we have an exponential growth curve of y equals 3 to the x, and we have a horizontal line, a y equal to negative 1 constant function, and these two graphs do not intersect, which means we have non-real solutions because powers must be positive. So coming out of this equation, we have x is contained in the empty set of real values, and the only solution is x equal to 2. Now we can take a look at the logarithmic question, and we can see something slightly different here. I'll just erase this. And over here we have, first of all, a domain restriction, and second of all, we have x showing up in two different places, but we can combine the two logarithms into one using our logarithmic properties. We end up getting log base 10 is of the product of the two powers. Be really careful about your brackets here. And all of that expression is equal to 1. So in order to solve for x, we need to undo what is being done to it from the outside in. So we undo logarithmication base 10 by exponentiating base 10 on both sides. So 10 to the and log base 10 cancel, and we have this quadratic is equal to 10. There are a lot of mistakes here with this being called 10 or 1 or 0, just getting kind of the exponents and the powers completely mixed up. So then we can expand, and we should be able to expand this in one step. X squared minus x plus 2x is plus x, and then minus 2 is equal to 10. Another common mistake people made here when solving was to add 10 to both sides, and so a lot of people got an 8 over here, which meant that when you tried to factor, you couldn't, and you ended up solving by quadratic formula. Here this does factor. We get x plus 4 times x minus 3 equal to 0. And by the zero product property, either the first factor equals 0, which means x equals negative 4, or the second factor equals 0, which means x is equal to 3. Now a lot of people circled this, which, if I read minds correctly, is to say that this is the answer and this isn't. That's not really communicated well enough. This is the answer, so we could say, we could still put a box around here, and we could say that this is extraneous, but we need to say why this is extraneous, and for those of you who didn't find the domain, you've got no reason to choose this. Again, a lot of people simply chose this because this is the positive x value, but we're not actually saying that x has to be positive, we're saying that powers have to be positive. If the power is just x, then x being positive is equivalent to the power being positive, but x by itself is not the power. So any conclusion that just says x has to be positive is a false conclusion. So you want to say this is extraneous, and you can say this is contained in the domain, and therefore this is the solution. And we can say this is not contained in the domain because this value is not greater than 1. In number 15, we want to graph a logarithmic function, and I'm just going to rename f of x with y. And as often when we have a logarithmic expression, we set it equal to something, and from that equation we rearrange to exponential form. I'm going to do that as well. Base to the exponent equals power, so this equation can also be written as 2 to the exponent y is equal to the power 3 minus x. Now we know that powers must be positive, and so powers being positive means that 3 minus x must be positive, which means that 3 is greater than x. So our domain is going to be x less than 3. The range is the set of y values. I see a lot of people putting x contained in when you're finding the range. Make sure that you're using y for the set of range values. Since y is in the exponent and there are no restrictions on exponents, y can be anything. So y is contained in the reals. The asymptote comes from the power being set equal to 0. It's the boundary between where we have no graph and where we do have graph. And so in this case, the power equal to 0 would be like saying 3 minus x is equal to 0 because 3 minus x is the power. And so the equation of the asymptote is x equal to 3. And x equal to 3 is a vertical line, so we have a vertical asymptote. A lot of people don't really know the difference between their exponential and logarithmic graphs, and I saw a lot of x equal to 3 horizontal asymptotes, and I indeed saw exponential growth or decay curves here. So be really mindful of that. Please label your axes x and y. And then to come up with the intercepts, just like we always do, if we want to find the x-intercept, we set y equal to 0, and if we want to find the y-intercept, we set x equal to 0. And so doing so one at a time, you can either use the original version of the equation, the logarithmic version, or the rearranged but equivalent exponential form. I think I'm going to substitute y here equal to 0. And so for the x-intercept, I'll use this form. 2 to the 0 is 1. And then solving 1 equal to 3 minus x, I get x is equal to 3 minus 1, so x is equal to 2. So I have an x-intercept at 2, 0, which is going to be right here, which is good because that's in my domain. I don't have any graph over here when x is to the right of 3. So that's good news. And then to get the y-intercept, I want to set x equal to 0, so I will actually do that in the first form of the equation because I'm solving for y, and y is already isolated. So substituting 0 here for x, we get that y is equal to log base 2 of 3. In fact, that's actually even easier because since 3 is not a perfect power of 2, that answer is simplified. But I know that 3, the power of 3, lands between the perfect powers of 2 that are 2 and 4. So log base 2 of 2 is less than log base 2 of 3, which is less than log base 2 of 4. So this y-intercept lies between 1 and 2. So I'm just going to plot somewhere between a height of 1 and 2, that y-intercept. Now to come up with some other points, I can either substitute for x and solve for y, or substitute for y and solve for x. And I think it's easier to substitute in the exponent and work out the x value. In fact, I could just rearrange this equation a little bit to solve for x. So if 2 to the y equals 3 minus x, then x is equal to 3 minus 2 to the y. You can make a table of values if you want, or you can just be really careful with substituting in and recording the answers. So if y is equal to 0, we already got the x value of 2. If y is equal to 1, then 2 to the 1 is 2, 3 minus 2 is 1. So I'm going to get a point at 1 comma. Wait a minute. Oh yeah, that's right here, 1 comma 1. If y is equal to a height of 2, then 3 minus 2 squared is 3 minus 4, which is negative 1. And so that's this point over here, a negative 1 comma 2. And this is easy, so I'll just keep substituting nice neat values for y and solving for x. 3 minus 2 cubed is 3 minus 8, which is negative 5. And so I have lots of points. I've actually run out of space. Negative 2, 4, negative 5, comma 3. And so I can plot my logarithmic curve, which keeps increasing when we go to the left, and then we have running along the asymptote down here. Make sure to put arrows on the ends of the graph. I won't list my other points here, I'll just write them beside the plotted points on the graph. And so be really, really careful about your substitution. You need to give yourself lots of space when you're doing this. And I think that's part of what gets in people's way. You try to cram things in. So spread out, communicate really well, and step by step, all of these pieces fit together like pieces of a puzzle. In number 16, you had two options, a slightly easier question and another one that we had done with a C value, a horizontal asymptote that was not at the x-axis. You have to read the instructions. A lot of people did not come up with a table, a graph. They came up with a pre-existing exponential equation or formula, which I've asked you not to do, and I've asked you to answer the problem, leave the answer in exact form, and then represent the solution in the table and on the graph. Failure to do that meant that you didn't get the full modeling and problem-solving points. So for part A, we have the temperature question. We define our variables in the table of values, and so we have x and y. X is going to represent the time in minutes, and y is going to represent the egg temperature. This is all part of the defining, and not everybody gave a quantity and the units for each of x and y. Now at time 0, we know that the egg temperature is the same as the water temperature when the egg is removed from the boiling water. 5 minutes later, the temperature is found to be 38 degrees. And as time goes on forever, the water temperature and the egg temperature would merge to a constant 18 degrees Celsius. This is our value for C, which from our model y equals a times b to the x plus c is the vertical translation of the horizontal asymptote. So our model so far is y equals a times b to the x plus 18. Later on, we're asked to answer a question, how much longer will it take? So technically it's how much longer after 5 minutes, but I was happy just to answer for x when the temperature is 20. So technically I wanted to find the increase from 5 until this time by answering the question, but I'll be satisfied with at what time did the egg temperature reach 20 degrees. So from here we want to determine our model and come up with a graph. So the graph is going to be an exponential decay graph. We have a horizontal asymptote at y equal to 18. So let's plot that first. And we don't have to be so precise with labeling the points and the values along the axes. I want to make that asymptote come a little bit closer as time goes on. And we can see that this is some point at time 0, but in order to figure out we have time 0 and 98 degrees. Yeah, that's fine. And so, but that doesn't mean that a is equal to 98. So when we substitute in 98 for y and 0 for x, we end up getting that 98 equals a plus 18, which means that a is equal to 80. So our model so far is y equals 80 times b to the x plus 18. So we've used the first point. Now I'm going to use the second point and substitute in. When x is 5, y is 38. So 38 equals 80 times b to the 5 plus 18. Again, solving, I'll subtract 18 from both sides first. So we get that 20 equals 80 times b to the 5. 20 divided by 80 is 1/4. And here we don't use logarithms to solve for b because this is not an exponential equation because the variable is in the base and not in the exponent. So we use roots or fraction exponents. We can raise both sides to the exponent of 1/5, which is the same as taking the 5th root of both sides of the equation. And so we have that b is equal to 1/4 to the 1/5. I'm going to change 1/4 to 4 to the negative 1, all to the 1/5, which is 4 to the negative 1/5. Or I could change 4 to 2 squared and make this 2 to the negative 2/5. We substitute that in and we come up with our model now. So the model is going to be y equals 80 times, I like the 2 to the negative 2/5, all to the x plus 18. And then the simplest way to write this is 80 times 2 to the negative 2x over 5 plus 18. The reason is I like the base of 2. I know a lot of the numbers and the perfect powers of 2, so it makes it easy to work with approximations. A lot of people used a model that involved e to the rx or e to the kx or something like this, which meant that you had really, really complicated bases and almost impossible to approximate. So now the next question is to solve for x when y equals 20. I asked that you write that out. Solve for x when y equals 20, so that we're really being clear in our communication what we're doing. 20 equals 80 times 2 to the negative 2x over 5 plus 18. Now, if you watch the videos on 3.5, you would have seen lots of examples of the table, the graph, and the solving in stages. So now we subtract 18 from two sides. We get 2 equals 80 times 2 to the negative 2x over 5. We divide both sides of the equation by 80. And we end up with 1 over 40 equals 2 to the negative 2x over 5. Now I'm going to rewrite 1 over 40 as 40 to the exponent of negative 1. And I'm going to reciprocate both sides of the equation, or raise both sides of the equation to the exponent of negative 1, which is going to deal with these negative exponents. I now end up with a simpler looking equation that says 40 equals 2 to the 2x over 5. Now, in order to solve for x, I need to undo the exponentiation base 2 by applying log base 2 to both sides of the equation. So this gives me log base 2 of 40 equals 2 to the, cancels with the log base 2, and I'm simply left with the exponent 2x over 5. Then to solve for x, I can multiply both sides of the equation by the reciprocal of 2/5. And therefore we get that x is equal to 5/2 times the log base 2 of 40. Now we want to know if this answer is reasonable. To be reasonable, we need the time that we just solved for to be more than 5, because the temperature is decreasing and has to be in line with the temperature values 98, 38, 20. So in order to approximate this, I might want to know something about how big log base 2 of 40 is, which means I want to know the perfect powers of 2. So if I recall my basic number facts, I have 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, getting closer, and then 2 to the 6. And so my power of 40 lies between the perfect powers of 2, namely 32 and 64. And so what is the exponent on 2 to get 32? Well, that exponent is 5, so this is 2 to the 5, and 64 is 2 to the 6, which means that log base 2 of 40 lies between 5 and 6. And so, if this is an answer between 5 and 6, then multiplying by 2.5, I'll write it like this. So x is contained between 2.5 times 5 and 2.5 times 6, which is more than 5, because 2.5 times 5 is more than 5. And so x is more than 5 minutes, and therefore the answer is reasonable. So this is really the last step that we were looking for here to see if our answer without a calculator makes sense. So all of that was required for full marks in part A. We also wanted to go back somewhere and plot these values. So if we had the 5,38, that would be somewhere over here. And then our final answer would be some temperature over here, and that would be 5/2 log base 2 of 40, comma 20 degrees. And we could just put that number in here. 5/2 log base 2 of 40. So the ability to approximate that easily is all dependent on you choosing a good base. And using the pre-existing formula may be something that a previous course or an outside tutor has taught you using e to the rx. It's not really conducive to understanding and approximating and judging the reasonableness of your solution. Part B is the same kind of modeling. We have exponential decay again here, and x is going to be time in years. Again, make sure that you're defining your variables. I said you don't have to write full sentences, but do make sure that you're putting the quantity as well as the units. Years is not the quantity. Time is the quantity, years is the unit. Mass of the radioactive substance is the quantity, and the units is grams. Units are grams. And we have y equals a times b to the x plus c, but the reason this is a simpler problem, it's because the c value is equal to 0. So when we extract the information from the word problem, we see that at time 0 we have 60 grams, 0 years 60 grams. 2 years later we have 12 grams. And then we want to find out when, so we want to solve for x when y is equal to 6. And if time goes on, if time approaches an infinite number of years, the mass would approach 0 grams. And that 0 is why we have a c value of 0. We have not vertically translated the horizontal asymptote for the exponential decay curve. So we're going to solve for a and b, first of all by substituting 60 and 0 for y and x. And this gives us that a is equal to 60. It's for this reason that a lot of people got the previous a value wrong. They thought that whenever x is 0, this number is a, but it's not true. That's a special case that doesn't always apply. So do all of the steps properly when you're solving. So we have a is 0, so we now have our model as y equals 60 times b to the x, and we use our next ordered pair of 12 for y and 2 for b to solve. 12 divided by 60 is 1/5. And that's equal to b squared. So when we solve, we take the square root of both sides, and we end up getting two solutions for b. b is either negative the square root of 1/5 or positive the square root of 1/5. But bases can't be negative, so we exclude the first option, and base is only positive 1/5. Now we can go and say that 1/5 is 5 to the negative 1, and then the square root is raising to an exponent of 1/2, so I think it's easier to write base as 5 to the exponent negative 1/2, which means that our algebraic model is 60 times 5 to the negative 1/2 all to the x, or 60 times 5 to the negative x over 2. Now, if this was 3 years, we would have had a 3 here in the denominator instead, so be really, really careful how you're solving. We can also come up with our graph here. We have a horizontal asymptote on the x-axis, and we have our exponential decay curve passing through those points. And so don't worry too much about the points, just get the shape right, and then you can plot the points afterwards. 0, 60, and then 2, 12 would be much lower down according to my picture. So try to get the picture somewhat accurate. Okay, then we go on and we answer the question, when? Solve for x when y equals 6. So I've asked you to write that sentence out. Solve for x when or such that y is equal to 6. And we substitute into our model, which I will just rewrite here. We substitute 6 for y, and we solve for x. 6 divided by 60 is 1/10. 1/10 is the reciprocal of 10, and so if we reciprocate both sides, I can show reciprocating by raising to the exponent of negative 1. I can show reciprocating by making it 1 over. That's a bit messy, and so I'm actually going to raise both sides to the exponent of negative 1. Then I end up getting a tidier equation without any negative exponents and without any fraction, base, and powers. Then I want to undo what's being done to x in the reverse order of what's being done to x. So the outer thing being done to x is exponentiation base 5. So to undo that, we apply logarithmication base 5. So we get log base 5 of 10 is equal to log base 5 of 5 to the, which cancel, leaving us with x over 2. And then we multiply both sides of the equation by 2 to get that x is equal to 2 times log base 5 of 10. Now this is a much easier expression to evaluate or to approximate. I can take that coefficient as an exponent on the 10, and I can get log base 5 of 10 squared or log base 5 of 100. And so since I know my powers of 5, 5 to the 1 equals 5, 5 to the 2 equals 25, 5 to the 3 equals 625, I know that the power of 100 lies between 25 and 625. So I know that x is going to be contained between 2 and 3. And so if I look back to my table of values, I judge to see if that makes sense. I want my time for the mass to become 6 grams to be more than 2 years. And my answer for x is, that's minutes. It shouldn't be minutes. I think this is in years. And so x is more than 2 years according to my approximation here. So therefore, since x equals log base 5 of 100, which is contained between 2 and 3 years, and is more than 2 years, as we can judge by the graph in the table, the answer is reasonable. And again, we're looking to see that we have the flexibility to rearrange the logarithm in an appropriate way that's easy for us to approximate. So log base 5 of 100, comma 6, and that point would be halfway down over here. Log base 5 of 100, comma 6 would be somewhere after the 2-year mark. Okay, so that would be for a B score for the problem solving and the modeling. This last question is the only true non-routine question because the modeling questions of the previous, number 16, A and B, were done in the 3.5 unit and in the video. So when we're taking a look at this, we want to solve for x. We notice a couple of reasons why it's difficult to solve for x. First of all, x shows up in the power and in the base. So x shows up in more than one location, which, as we saw for question number 14, made the equations harder to solve. Secondly, we have different bases of the logarithms, and we can't really use any of the logarithm laws when we have different bases. So those two problems actually suggest the strategy for solving the problem. Let's get the same base, and let's condense into a single logarithmic equation. By that I mean a single base, a single power, and a single exponent. Once we do that, we should be able to rearrange and isolate for wherever the variable is. So with that in mind, we see that x is both in the base and in the power, and we know that bases must be positive and not equal to 1. So this suggests that x has to be greater than 0 and x can't be equal to 1. We also know that x is in the power, and we know that powers must be positive, which suggests that x, which is the power by itself, has to be greater than 0. So overall, the domain of this equation or function or expression is that x has to be contained from 0 to 1 or from 1 to infinity. So any negative value, 0 value, or 1 value for x is not defined, or it's not a solution. At this point, I want to point out a common error that a lot of people made here. People wanted to condense these two logarithms into one, which is a good thought, but it was done incorrectly. It was a violation of the order of operations, which says here we're taking the logarithm of two expressions first and then multiplying, and it was turned into multiply first and then take the logarithm. These two things are not equal. Instead, we know that there's a logarithm law that says if you're multiplying two powers, that's equal to the sum of the two logarithms. And so log base x of 3 plus log base x of 4 is not the same as log base x of 3 times log base x of 4. So since this is equal to this, these two things cannot be equal. So that was a very, very common misconception, stemming all the way back to Algebra 1 and order of operations. If you're not getting clear on that, please let me know. Let's work on it. Okay, so how do we deal with that if we can't condense those two? Well, the fact of the matter is, we still have this other logarithm with a different base. Let's get all the bases the same. And my preference is to have a number in the base as opposed to a variable in the base. So let's do a change of base. Let's change to base 2. And since we have 3 logarithms, we're going to do it one at a time. Since we have logarithmic form, we're going to do the change of base formula for logarithms. In other words, log base, let's say w of a, is equal to a quotient of 2 logarithms. The a goes on the top and the w goes on the bottom. Those were often mixed up for some people. And we can have whatever base we want as long as it's the same base top and bottom, and of course as long as the base is acceptable, positive and not equal to 1. So we're going to change each of these expressions according to this change of base formula. Now the first logarithm, log base 2 of x, already has a base of 2, so I don't need to change it. Log base 2 of x, not sure what I just said there, multiplied by, now I'm going to change this one to a fraction. with log base 2 in the top and the bottom. And the power 3 goes in the top and the base x goes in the bottom. This is actually quite convenient because we notice that we've got a numerator and a denominator that are the same, so they cancel or reduce. The third logarithm, log base x of 4, is also being changed according to the change of base formula. So we have log base 2 in the top and the bottom, and the power of 4 goes in the numerator, and the denominator of, the base of x goes in the denominator. And all of that is equal to 1. Well, if you remember, one of the problems that we faced earlier on was that x showed up more than once in the equation, and this has actually gotten rid of that problem. Now x shows up only one time. We also have a simple logarithm here. What is the exponent on base 2 to get the power 4? Well, that exponent that we need is 2. So this expression is equal to 2. So I'm just going to tidy this up a little bit. I have 2 times log base 2 of 3 divided by log base 2 of x, and all of that is equal to 1. I can take this coefficient and bring it up as an exponent on the 3, and I can multiply both sides of the equation to clear the denominator. So we multiply by log base 2 of x on the left and by log base 2 of x on the right. Another common mistake or communication error I have seen is when we have one equation equal to another equation. If we take a to the w equals m, and we want to convert it to logarithmic form, log base a of m equals w, we can't say that these two expressions are equal. You're essentially saying that m is equal to w, and that's not true. What it is you want to do instead is to put an implies arrow like this. Whenever you want one equation to be equivalent to another equation, we use this symbol instead. Similarly, if we want to say that an expression like 2 plus 3 is equal to 5, we do not use an arrow, whether it's a single or a double arrow. We use a regular old equation here. So whenever an expression is equivalent to an expression, we use equals. But whenever an equation is equivalent to another equation, we use the double arrow. Okay, that's a very, very common misconception. I'd say that at least half of people are misusing arrows and equal signs. So back over here, we see that the denominator no longer contains an x, and the 2 comes up as an exponent. I'm just going to cross it off here. So now this says log base 2 of 9 is equal to log base 2 of x. And by the one-to-one property, we have an exponent on the left, an exponent on the right. They have the same bases, therefore the powers must be the same. And as a result, we get that, so I'll squeeze it in, x is equal to 9. Now we need to double check, is that part of the domain? Yes, 9 is greater than 1, so this satisfies the equation. So take a look at all of the questions here. If you've got any questions, let's discuss them, let's clear up your misconceptions, and sometimes we need to go all the way back to Algebra 1 or to Algebra 2 to find the source of the misconceptions because they're not always rooted, in fact not usually rooted, in the current course. Okay, thanks for checking out the video and let me know what your questions are.